Okay, we're back. Sorry about that sloppy whiteboard use before. I guess by now I should know one video, one whiteboard full of information. That's okay. So these are just going to be a little shorter, which is fine because this particular chapter is a lot of math and there's some chunks we're not even going to do. Okay, so let's go on to the second part of this chapter, and that's dissolved oxygen. And you'll see in the book and also on the slides that I have here for this section, this is letter B, so we're in section 10.4 if you want to label that up there, DO section 10.4. If you want to label that, that's fine. And there's an infographic there that says some sketchy grammar. I think that sentence at the bottom. What is dissolved oxygen and how it measured? Okay, not sure what that's about. The key thing is, or a few key things, is oxygen is an oxidizing agent. That might be, well, one of those, well, duh comments. It's oxygen. That's why we call it oxidation. It's something that oxidizes other things. So that's kind of an obvious thing to say, but there's a little bit more to it than that. Like rust is oxidation. But in the process of oxygen being the most important oxidizing agent in natural waters, therefore, oxygen is reduced in natural waters. So there's oxidation rate, there's reduction rate. So we have to take into account, and I'm not going to go through the balancing of the redox equations here. You can do these if you want to. So you can balance this in an acidic solution and in a basic solution. Now, a couple things that I think we've addressed this multiple times in the course. The book, if you're using the book and depending on who you had for general chemistry and where you had general chemistry, just checking the clarity there. You've learned a couple different methods for balancing redox reactions. You might have learned what was called the half reaction method, which is the method we teach at Shippensburg University, or you might have used what's called the oxidation number method, which is what the book references in the appendix. It doesn't matter to me what way you do it, as long as you understand how to balance oxidation reduction reactions. And there's always review problems for that. You can always see me for extra help. So in an acidic solution, oxygen, now we're going to aqueous oxygen, so we have to do some Henry's law for that, becomes water. So oxygen becomes water in an acidic environment. You can go ahead and try to balance that equation, and you should come up with, and again, I'm not going through this, I was looking at my notes. It's not that hard, I don't think, when it comes to this. And remember, reduction is a gain of electrons. Oil oxidation is loss of electrons. Reduction is a gain of electrons, left side. And that's what the equation would look like for in an acidic solution. Acidic meaning H+. In a basic solution, oxygen becomes hydroxide ions. That's actually pretty important. Pretty important. And in this case, it's almost like the opposite of the other one, sort of. No, it's not a great way to put it, but it's somewhat accurate. That's the chemical equation. So in both cases, oxygen is reduced. And it depends if it's an acidic or basic solution. I'm just emphasizing, we're not talking about gaseous oxygen anymore. We are talking about aqueous oxygen. Okay. So I want to combine, that's just the basic point of this one. Let me see if I missed something in the notes here. Yeah, okay. Number 2, I think this is number 2. Slides. Yeah, is a dissolved oxygen solubility. And you can see this here. And yeah. So on this slide, this is the last one we're going to do with this video. We're just going to redo problem 10-2. Stop the video if you just want to do it yourself. And we went through units before. Just remember that parts per million is milligrams per liter, parts per billion is micrograms per liter. And the graph that I have there, I don't think that was in the book, is this shows you that, well, as the water gets warmer, well, you have less dissolved oxygen, milligrams per liter, so ppm. Okay, well, that's something that we call, well, it happens naturally, but if a chemical plant, a nuclear power plant like 3 Mile Island heats the water, we call that thermal pollution. So that's anthropogenic. So warming can happen either naturally but the important part is if the temperature gets higher, the dissolved oxygen goes down, which has huge effects for the ecosystem. So we're just doing some of the math behind this. Okay, so in this case, we are just going to redo problem 10.2. Okay, so what's the equilibrium we're talking about here? And I think in this case, okay, so the point is this. The point is to calculate in ppm the concentration of dissolved oxygen at sea level, dry air, at 25 degrees Celsius. So under those conditions, what is the DO content in ppm? Because that is how most of the world thinks about it. How much is in the water in terms of ppm? That's the way we think about naturally occurring things in water, naturally occurring species, excuse me, and then also pollutants. So we want to get into this mindset. Okay, so what are we talking about? So the chemistry is pretty straightforward. It's oxygen gas in equilibrium with oxygen in the aqueous state. And there's some information we need. The partial pressure of oxygen, we're going to take this as approximate. And I think I told this story before, is recall from kinetic molecular theory, which treats gases as billiard balls smacking into each other, that air is approximately 20% oxygen. So it stands to reason that the partial pressure of oxygen under most conditions would be about 20% of an atmosphere. So this is a reasonable number. That just being out and about, that's a reasonable partial pressure. So that's specifically at sea level. If we were in Denver, that would be very different. And it also matters how humid it is. Okay. If it's humid and there's a lot of H2O in the air, the partial pressure of oxygen goes down. It's basically diluted by the humidity, which is why it's a little bit harder to breathe outside when it's very, very humid out. Those of you that live in humid areas and run or ride a bike in humid weather, you feel that. So that's the reason. So we need to know that. That's not a difficult number to find. And we would also need to know the Henry's law constant at a given temperature. And this is at 25 degrees C, a fairly normal temperature. Okay, so the rest of this math essentially becomes unit conversion. So if we apply Henry's law, we don't have to rearrange anything. So the molarity, so if we just do Henry's law, that's going to give us molarity. We want milligrams per liter, so we'll have to take moles and make it milligrams. It's the unit conversion problem. So let's just do the math real quick. I guess we solve this out here. So we take the Henry's law constant times the partial pressure, and let's just string this together. So it's 1.3 times 10 to the minus 3. That's a pretty small Henry's law constant, so it's not very soluble. Let's compare that to benzene or phenol if you want to. So 1.3 times 10 to the minus 3 molarity millimolari per atmosphere, Penn's law constant, times the partial pressure, 0.21 atmospheres. And that gives us, what? I came up with 2 points, I think I did pretty sloppy significant figures, but I'm going to round it to 2 significant figures at the very end. Yeah. So 2.73 times 10 to the minus 4th moles of oxygen per liter, and we want milligrams per liter, which is the same thing as ppm. That's eventually what we want. So not too bad. So what we have to do then is take moles, convert it to grams. A mole of O2 is about 32.00 grams, and then we know that, let's see, a gram is 1,000 milligrams, or you can say 1 milligram is 10 to the minus 3rd grams. It doesn't matter which way you do it. And I think the answer you get if you do all that math is 8.7. And did I want to check this. Is that about right? 25 degrees Celsius, and just look at this graph that I gave you. So 25 degrees Celsius go up and over. It's not exactly matching up with the graph, but that's okay. I'm not sure where the graph came from. But you know, it's in the ballpark, I think. That's fine. And the last thing I'm going to mention here is it was a conceptual problem that I was trying to figure out why I even had this on here. And I'm just going to read the question rather than write this down here. I just put this as a question to get started. At what temperature is the concentration of oxygen about 5 ppm? That, why 5 ppm? 5 parts per million is the threshold of aqueous oxygen concentration that fish can sustain their living on. So if it gets below 5 ppm, you start to get big fish die-offs because of the dissolved oxygen content. That can be one reason why you have a fish kill. Lots of reasons why you can have a fish kill, but usually it's because the dissolved oxygen drops below around 5 ppm. And I think that was just a graph question. Let me double check that. Yes, that was just a qualitative question. So, how hot would water have to be? This is just, you don't need to know any science to do this one, just reading a graph. 5 ppm, that's pretty warm. What is it, like 55 degrees Celsius, something like that? That's pretty warm water, but there's other ways for the dissolved oxygen to be used rather than just temperature. Algae, all kinds of things that could happen there. All right, so that's the first couple sections of this, and then we will pick up with the next section on biological oxygen demand with the next video.